So we want to make the connection here between oscillations that we just learned about and waves. And so it's useful to look at a couple of simulations here. So we're going to start with this first one, which is not a simple harmonic oscillation. It's just a pulse. So you can see a hand goes up and down. Actually, it just goes up and comes back to where it started, and that sends a pulse along this set of particles. You can think of it as particles in a rope. And what this, I'll send it again, what this simulation is showing you is the pulse as it travels, and then also data for just this red dot that's right here in the middle of the screen, the position versus time for the red dot. So that's just a pulse that gets sent along the rope, for example, and it travels down. It becomes a wave and travels down. The second one is going to show you the same thing. So we have a pulse that's going up, but you can think of the hand that's moving as being generated by something that's oscillating up and down with simple harmonic motion, right? So you can think about, now we're seeing the motion of the red particle and it's going up and down. Notice the red particle isn't changing its position horizontally, it's just going up and down vertically. You can think of this like a wave in a stadium back when we could all be in big groups and you set up a wave going around the stadium. You don't get a different seat. You stay in the same location relative to the field if you're at a baseball game, for example, or football game, but you go up and down. So this red dot is going up and down as the wave gets to it, but the hand is also just oscillating up and down. So this hand is exhibiting simple harmonic oscillation because its motion could be described by a sine or a cosine, and the red dot in response, when the wave gets there, notice it starts oscillating with a position versus time graph that works just like oscillations. Now this is called a transverse wave. We're going to see one more. This is a longitudinal wave. The hand is still oscillating, right? This is just a pulse, actually. But you could have the hand moving back and forth, and that would be a longitudinal wave, a compressive wave, as it's called. And that's what sound waves are. Okay? And now the position that it's showing you is position. If you notice, this scale is going from basically 12.5, so the position of the red dot, now it's moving back and forth. You can think of it as slipping over one seat, coming back to the middle, and slipping over the other way. So that's a compression wave. And finally, we can see sort of a combo happening on a spring, slinky, for example. We've got both a transverse up and down along with a compressive wave. So you can create in a slinky just a compression wave, but you can sometimes create sort of both of these. And this doesn't show a graph because it's not sure whether we should show the up and down position change or the X and Y position change. We can see how this then translates to the idea of waves in water. So here's sort of the picture. The top of the wave you're used to, it goes up and down. If you're a red dot, for example, sitting right under the 5, notice you go up and down and you do a little bit of translation back and forth, but you still end up basically the same place. Whereas when you're deeper in the water, down here at the lower greenish dots, it's basically just a compressive wave that's going back and forth. And you can see this if you look in the water column. You can see little bits of floating mass that just sort of oscillate back and forth primarily, not going up and down as much, but just back and forth is the wave motion that's happening at that level. So we can start to quantify the information that we have about waves, because that's what we do in physics, is try to quantify the information, describe it in a way that we can share that information or characterize what's going on. And so the first thing to notice is that, first of all, we would describe this as a transverse wave. And what that means is that the wave is traveling, this is the direction the wave is traveling. For example, it's traveling to the right string, but the waving motion is happening perpendicular to it, transverse to it. So this is transverse waves, okay, because the wave is perpendicular to the direction of motion. We can compare that then with this longitudinal wave where we have this compression. This is the direction of the wave travel, and then this is the direction of the oscillation of the wave. And notice again, as I said, this is our position, this is our horizontal position of this red dot, and so it's staying at basically 12.5 is where its home base was, and it got pushed, and then it's slowly going back to its home location at 12.5, which I am guessing is about here, 12.5 meters. And you can see it oscillates about a meter, which is a pretty big oscillation for something like this. Okay, so these are our descriptions, at least of the picture of type of waves, and And the transverse waves we think of like the top of water. So top of water, we can think of transverse waves. That's what light does. And mostly we'll be looking at this with like a slinky type or slinky rope oscillation. A compression or longitudinal wave would be a sound wave. As we look at that. Okay, so those are our two pictures. We can put this together to start to describe the wave. And so down here we sort of have a snapshot of the full wave, right? So you can think of this as like take a picture of a stadium where some people are standing up, some people are sitting down. That's a snapshot of the full wave, but it doesn't give the whole picture, right? Because the wave keeps moving. So this is a freeze frame of this motion. But from the snapshot, we can get some information. The first thing we can do is we can say the distance between peaks. So that would be like this. This is the distance between peaks or valleys, between peaks or valleys. That's going to be measured in meters, and that is a wavelength, and it's given by the Greek letter lambda. So that's the wavelength of a wave. That's the distance. So if you're on a raft and you're in the ocean and you're at a peak and your friend is also on a raft at another peak of another wave, right? So you're sitting here and your friend is sitting some distance away, then that is a wavelength distance, okay, at the top of the peak. And we're going to not look so much at water waves, but more pure sinusoidal waves because the calculations are easier. Now, what this top view shows is our typical, right, position versus time for one point. In this case, it is this point right here, and it's y position as a function of time. And so that's how high it goes. And so from both of these, we can get the amplitude. This is the amplitude of the wave, how far it goes in the y direction. And this also gives us the amplitude of the wave. For transverse, we can get the amplitude either way. For a compression or longitudinal wave, you would only get it from the position versus time information. So this is sit at one point, sit in your raft, one point, you on a raft. So I call this sort of the raft view, and this is the snapshot view. And the reason I want to differentiate those is because what we're looking at the top, they look the same. They both look like sine waves, maybe different spacing, but they both look like they're giving you the same information, but they're not. Because what this is telling you is this time between peaks, peaks or valleys, is our period, as we've seen before with simple harmonic oscillation. And so that is in seconds. And that tells you how fast you go up and down. And that's different than how far it is between peaks, right? How far it is between peaks is a distance, but how fast you go up and down is different. Now they are connected to each other, which we'll get to in just a minute, but I want to sort of finish this out. So the time between peaks is the time in seconds, so how long it takes between waves. So you're at the top of a wave, how long is it going to take before you go back to the top of the wave again? And then the frequency, just to round out our definitions, the frequency is 1 over the period, just like we've seen before, which is 1 over seconds, which we also call hertz, abbreviated as Hz. Okay, so this top view is what you've seen before. This raft view, if you like, is what we've seen with simple harmonic motion. Everything carries over from that. We can describe it as A sine omega t or A cosine omega t. That still works for this top view. Okay, these things are connected. It depends on how fast the wave is moving. That tells you this relationship between wavelength and this time. It turns out that the speed of the wave speed of the wave, this doesn't tell you the direction, the wave speed is equal to your wavelength times your frequency. And just to check the units, the wavelength of lambda is meters. The units of frequency are 1 over second, so that works out. And the wave speed depends on the material. Depends on what the wave is traveling through. And so if it's traveling through a slinky, that depends on the stretch of the slinky, as it turns out. If it's traveling through water, it depends on the properties of the water. Salt water or fresh water, temperature of the water, but basically we've got a pretty good picture for wave speed in water. Sound, it depends primarily on the temperature. So we get our wave speed depending on what the wave is traveling through, and then the frequency gets set by the hand, right? This hand going up and down sets the frequency, and then the wavelength shows up as a relationship between these things, set by hand or whatever is oscillating. Okay, so that could be your hand, it could be your vocal cords to create a sound, it could be a tuning fork that waves back and forth to create a sound, it could be a string on a stringed instrument that's oscillating back and forth to create a sound. And so it's that oscillation that gives us our frequency. And then that oscillation, the hand going up and down, the string going up and down, that then generates a wave in whatever's nearby. It's like it hits the nearest atoms and they hit their nearest neighbors, which hits their nearest neighbors, and they send the signal on along. Okay, so this is the general picture of a wave and how it connects to simple harmonic oscillation. It's the oscillation that sets the frequency, and then depending on what material is nearby, material that's nearby to pick up the oscillation, to get the oscillation, and let it propagate to create the wave. and then the wave speed depends on the material, and then from that you can find the wavelength. So I sort of, even though the wavelength is often the easiest to measure because you can see it in a snapshot, it's what's sort of left over after your hand or whatever oscillates back and forth, and then it depends on the material.